Hi, this is Abhijit and you're watching AB Study Circle. Do like, comment, share and don't forget to subscribe so that you don't miss any video from AB Study Circle. In this video, we are discussing about a question that has been asked in CSVTU University Exam in 2008 and it is also from your Unsolved section of your Engineering Thermodynamics book written by PK NAG. The question is like this: two streams of air, one at 1 bar 27 degrees Celsius and velocity of 30 meter per second, and other at 5 bar 227 degrees Celsius and velocity of 50 meter per second, mix in equal proportion in a chamber from which heat at a rate of 100 kilojoule per kg is removed. The mixture is then passed through an adiabatic nozzle. Find the velocity of the stream issuing out of the nozzle. The temperature of the air leaving the nozzle is 27 degrees Celsius and its Cp is 1.005 kilojoule per kg Kelvin, which we already know because it's an air, right? Okay, so here we see that there is two streams which is going into a mixing chamber. Then from there, that mixture of the stream, then it is being introduced into a nozzle from where it is being used to increase the velocity, because the nozzle is used to increase the velocity of the stream. So the question wants us to find out the velocity of the stream, right? So let's understand this question with the help of diagram. Okay, see, this is a stream chamber. Okay, this is the chamber where two streams of air are going inside, and then it mixes like this, and it is being introduced to a nozzle which is adiabatic in nature, like this, and again the output of this nozzle is this, right? So if we say that these two streams are at state 1 or condition 1 and condition 2, it mixes in the chamber to produce the mixture at condition 3, and this mixture which is at condition 3 is introduced inside the nozzle, which gives an output of stream which is at condition 4. Okay, this is your nozzle, right? Now see what we are trying to do and how we will trying to solve this question is that we will divide this like this. We will first consider this chamber as a control volume. We apply our steady flow energy equation for this chamber. We will find out some relation with 1, 2 and 3. We leave that part there. We will again move further to this nozzle. We will consider this as a control volume where the input is the stream at condition 3 and the output is the stream at condition 4. We will apply a steady flow energy equation, and what relation we got from 1, 2, 3 and 3 from the chamber case, we will use that to find out the unknowns at condition 4, which we will get the velocity, the unknown, right? Okay, so we got a rough idea how we will solve this question. So let's start with the given things. Okay, we have pressure at stream 1 as P1, okay, that is 1 bar, which is equal to 100 kilopascal. Okay, 100 kilopascal, 1 bar, it's 1 bar, so 100 kilopascal. Okay, so T1 we have 27 degrees Celsius, which we convert to Kelvin by adding 273. It will be 300 Kelvin. We have velocity as 30 meter per second. Okay, it is the condition of stream 1. The condition of stream 2 is 5 bar, which is 500 kilopascal. Okay, T2 as 227 degrees Celsius, which is nothing but 500 Kelvin. C2 as 50 meter per second. Also, it says that the heat removed at rate of 100 kilojoule per kg. So heat removed as 100 kilojoule per kg. Okay, this is given. Again, the leaving temperature of the leaving stream at 4 is given as 27 degrees Celsius. So we have T4 as 27 degrees Celsius, which if we convert into Kelvin, it will be 300 Kelvin. Okay. Also, we have Cp as 1.005 kilojoule per kg Kelvin. Okay, this we got from here. Now we have some assumptions. Assumption. The whole setup is horizontal. Assume this. It is not mentioned in the question, but you have to assume, because there is nothing that mentions anything related to potential energy or datum height. So we assume that the whole setup is horizontal. So potential energy change is negligible and it can be neglected. Okay. Now let's start. So first, mass balance. Starting with our chamber 1. This is a chamber which we'll be considering as a control volume. Now, in the question it says that the two streams of air mixes in equal proportion. So, let both the stream mass flow rate as m dot kg per second. Let both the stream mass flow rate as m dot kg per second. Okay. So when it's both the mass flow rate as m dot kg per second, means the stream at condition 1 is m dot, have mass flow rate as m dot, and condition 2 as m dot. Okay. So for steady flow, what we know that if the flow is steady, that means the mass entering the control volume should be equal to the mass leaving the control volume. And if we consider this chamber as a control volume, the mass which is entering is m dot plus m dot. That is, the total mass which is inside, going inside the chamber, is 2m dot. So the mass leaving the chamber will be 2m dot. Right? Now, okay, so we got this. Now, if we consider nozzle part and considering nozzle as a control volume, the entering stream has a mass flow rate as 2m dot. So for steady flow, the mass flow rate leaving the nozzle will be 2 m dot. Okay, so we got this mass balance. So for chamber it will be m dot plus m dot is equal to 2 m dot, which we can imply as m1 plus m2 is equal to m3, right? Okay, now for nozzle that will be m3 should be equal to m4 mass balance, right? And m3 is what? 2 m dot. Then m4 will be same as m3, right? So we got this also. Now let heat flow rate is Q dot, capital Q dot, kilojoule per second. Okay, so for per kg heat removed will be equal to Q dot by 2 m dot, that is kilojoule per kg. Why Q dot by 2 m dot? Why 2 m dot? Because total mass inside the chamber is 2 m dot. See, heat is removed from here. How much heat is removed? Suppose it is the heat removal rate is Q dot, then in per kg term will be the heat which is removal rate by dividing the addition of these two mass flow rates, because the total mass flow rate will be m dot plus m dot, that is 2 m dot inside the chamber. Okay, so we got this also. So heat removal rate is Q dot by 2 m dot, right? And it is mentioned in the question as 100 kilojoule per kg. So this is equal to 100 kilojoule per kg. Okay, so this heat removed 100 kilojoule per kg is nothing but Q dot by 2 m dot. Okay, now for chamber case, steady flow energy equation. Okay, so we are applying our steady flow energy equation for our chamber case. Also I should mention here that in chamber there is only mixing taking place, there is no work is going through the chamber. Okay, so I will be putting like this so that we can easily understand. So there are two streams, so energies for condition 1 and condition 2 we have to equate with condition 3. So m dot h1 plus m dot c1 square by 2000 plus m dot h2. This is because we have neglected our potential energies, so we are neglecting for potential energy for the stream at condition 1. and for condition 2 it's m dot H2 plus m dot C2 square by 2000, and the heat removal rate is Q dot is equal to, in the right hand side the total mass is 2 m dot, right? Total mass flow rate is 2 m dot, so it will be 2 m dot H3 plus 2 m dot C3 square by 2000, and work done is 0 inside the chamber, so it's 0. Okay, so we have just applied the steady flow energy equation for the chamber, considering the chamber as the control volume. Now it can be written as m dot H1 plus m dot C1 square by 2000 plus m dot H2 plus m dot C2 square by 2000 plus Q dot. Okay, there I taking out 2 m dot as common, so it will be H3 plus C3 square by 2000 here. Okay, I have taken just 2 m dot as common. Now I will be bringing this 2 m dot on the left hand side, so this will change as H1 by 2 plus C1 square by 4000 plus H2 by 2 plus C2 square by 4000 plus Q dot by 2 m dot, right? In right hand side it will be H3 plus C3 square by 2000. Okay, so H1 can be written as, this is specific H1, specific enthalpy, so Cp T1 by 2 plus C1 square by 4000, okay, plus Cp T2 by 2 plus C2 square by 4000. This is your Q dot by 2 m dot, that is the mass flow rate, heat flow rate per kg, right, is equal to H3 plus C3 square by 2000. Okay, Cp is given in the question, T1 is given in the question, C1 is also given in the question, T2 is also given in the question, and we know that Q dot by 2 m dot is nothing but it's 100 kilojoule per kg, which is heat removed. So we just putting the values. 1.005 into T1 is 300 by 2 plus 30 square by 400 plus 1.005 into 500 by 2 plus C2 is 50 square by 400 4000, sorry, 4000, sorry, it is 4000, right? It is 4000. Okay, and this is the heat removed, means it will be minus 100, everything is in kilojoule per kg terms, and this is equal to H3 plus C3 square by 2000. Okay, so you can get here that H3 plus C3 square by 2000 is nothing but the value of this. So it comes as 302.85 kilojoule per kg. Okay, so we got this. Put at this as equation 1. Okay. Now, as I said that we will find out some relation between these three, and then we will use this nozzle as our control volume, and we will use that relation between 1, 2, 3 and 4 to find out a unknown, which is a velocity here. So for nozzle case, okay, for nozzle case SFEE, you know, for nozzle it is given that it is an adiabatic, so QCV is 0. As a nozzle, the work done is 0, and as I said that there is assumption that the whole setup is horizontal, so potential energy change is also 0. Okay, PE change is neglected. This is assumed. It is not given in the question, right? So steady flow energy equation will be, see, now for nozzle, the mass flow rate inside the nozzle is 2 m dot and outside is 2 m dot. So we will apply like this: 2 m dot H3 plus 2 m dot C3 square by 2000. Everything is nullified, and in the right hand side of the nozzle it will be 2 m dot H4 plus 2 m dot C4 square by 2000. See, this 2 m dot can be cancelled out, right? So it can be written as H3 plus C3 square by 2000 is equal to H4 plus C4 square by 2000. See, this H3 plus C3 square by 2000, we got the value as 302.85 kilojoule per kg. We can write this on this side, on the left hand side, right? We have this value of the summation of enthalpy and your kinetic energy head. So 302.85, and in right hand side it's H4, that is CP/T4. It can be written like this, plus C4 square by 2000. Okay, 302.85 is equal to CP, we know it's 1.005 into T4. It is given in the question as 27 degrees Celsius, that is 300 Kelvin. So we will multiply this as 300 Kelvin plus C4 square by 2000. From here we will get C4 as 51.96 meter per second, which is your answer.